right, well, we're going to get started here today. Thank you, everyone, for being here. This is really exciting. I normally don't see the line out the door that long, which is a very exciting thing to see. It really speaks to the importance of what we're about to hear today from our distinguished lecturer today. But my name is Daniel Tatchik. I'm the Executive Director here at the Scott Institute for Energy Innovation. And before we get started, just a quick housekeeping note. All of the utensils and the plates for the food that you're eating today are compostable. We try to keep our events as low waste or zero waste as possible. So if you could all do us a favor and please use the green compostable garbage bags out by the entrance and exit of this room, that'll really help us keep these events as sustainable as possible. So in case you're unfamiliar with the Scott Institute, we are the campus-wide energy hub for all things energy. So we give out seed funding to grow new energy research projects each year. We create and accelerate climate and energy research initiatives. What this means really is the Scott Institute is university-wide. We cover, topics that run the gamut in terms of business, economics, physics, chemistry, public policy. And so really it's up to the Scott Institute to ensure that all of these groups on campus that are studying energy from these different angles are coming together, and we are serving as that central hub to make that happen. We also support founders and innovative startups in energy and climate. We give out entrepreneurship funding, so much like our seed funding for research, we give out similar sets of funding for our entrepreneurs trying to start new ventures in energy and climate. And then lastly, we promote the CMU climate and energy community by hosting a range of events, such as the event you are at today for today's distinguished lecture. So really, these four things kind of come together to really help us catalyze the development of breakthrough technologies, systems, and policies that accelerate ourselves into a sustainable net zero energy future. And if you aren't already subscribed, we encourage you to take out your phones, scan this QR code. This is the best way to keep in touch of what's happening on campus at Carnegie Mellon around energy and climate. We do not spam you. We know emails are insane right now. We send this out once a month, and it's really the best place to get all of your information about what's happening in energy and climate at Carnegie Mellon once a month. One major plug I want to share with you all is next month, we will be holding our flagship event, Carnegie Mellon University's Energy Week. This year, the theme is reinventing the grid for our electrified future. And so today is kind of a sneak preview into kind of what that means. Looking at the various issues around the power grid, our aging infrastructure, extreme weather events, and new energy demands are really driving this transition, the reinvention of the grid. The folks that you see in this graphic here are really just some of our featured speakers, but please scan this QR code, visit our website, and you can see more of the speakers and more of the agenda that we have to offer at CMU Energy Week next month, and I hope to see you all there. All right, with that, I would love to invite Professor Jay Whitaker to the podium to share a few remarks and introduce today's speaker. So Professor Whitaker is a trustee professor in energy with a joint appointment in the Department of Engineering and Public Policy and Materials Science and Engineering at Carnegie Mellon, and he is also a former director of the Scott Institute. So with that, Jay, stage is yours.
Thanks so much, and I will not take too much time because we're already running behind because of the huge number of people that are here waiting in line. It's such a pleasure, though, to have Mateo here. We are kindred spirits in some ways because we both we're co-founders and leaders of aqueous electrolyte energy storage factories that are about 35 miles from Pittsburgh. Different time frames, but through that experience, we really have known the same people for over a decade. And so when I learned that he was moving here, which is amazing to actually come and work in Weirton and make this happen at Form, I was super excited. So we definitely have had a fair amount of socialization since he came, and it has been just great for him to join the community. Thank you, and Virginia, for both coming. It's been great having you here. Those of you who don't know who Mateo is, he actually, before doing Form Energy, was very prominent at Tesla. He incepted the stationary energy storage product at the Tesla back in the day, and also was director of powertrain there for a while and did a tremendous amount of work there, and then came out of that business trying to do something even more impactful and started Form. So he's been working really hard on that for 7 years, 8, 9 years, good heavens. Yeah, I was, I will say just thank you from Carnegie Mellon. Also, CMU has been a sub awardee on several forum-related research projects, including an RPE project that was very beneficial to both parties, and that was fantastic also. Mateo, surprisingly, or maybe not so much because he's obviously very polymathic and cross-cutting, undergraduate degree in economics from Harvard and a master's in theology from Yale. And somehow this is where you can end up. So without further ado, let's please welcome Mateo.
Thanks, Jay. Okay. Good afternoon, everybody. Thanks for coming. It's great to see you all. I'm happy to see that the tradition of leaving the front row open for a lecture remains consistent many years after I left the academic setting myself. I'm going to talk for about 30 minutes, but really what I want to do is make sure that we hear questions from you. Surely you came not just to hear me talk, but to maybe ask some questions and to engage in a bit of dialogue about the journey of starting a hard tech company and having those ties into academia, and then manufacturing as we do in the real world right now. It's been a fun journey, and I want to share a bit about that with you. It's also super challenging. It is not the easiest path to go down, but it has also been extremely so far rewarding, even as we are still launching the company in many ways. The company, as Jay referenced, was founded about 9 years ago. I had been at Tesla, and I'd been at Tesla for about 7.5 years there. When I joined, the company was about 300 people. When I left, it was about 30,000. And that's quite a different place to work, as you might imagine. And that's long enough also for me, working in that environment. You may have heard about Elon. He's somewhat of a hard driver. And my wife is here. I love my wife. I want to stay married to my wife. We have 3 kids, 3 lovely kids. I want to be in their lives. And also just, the arc was sort of done. That, what the company needed out of the leader for that particular function, right, had started and sort of stood up the energy effort, was something different than what I really wanted to do. I like to be at sort of the frontier of things and really, pull something out of the air in many ways. And I was able to do that mostly over nights and weekends at Tesla to start the energy business. But I also saw that very clearly there was something that was just a very large need that was unmet in the market for energy storage, and I'll get to that. And I found my co-founders, there are 5 of us. The co-founders actually ran through another academic in the world. His name is Yet-Ming Chang, and he's at MIT in materials science there. And Yet pulled sort of the 5 of us together. They had already, the four other guys had already started a company. And one of the co-founders of that company was Jay's co-founder at Acqueon. So that was the connection there. And we were all interested in this problem of long duration storage. How do you solve this multi-day duration storage challenge without having a presupposed solution in mind? And that was really what enabled us to come together as a team and say, let's just pursue the problem first and really understand it. Let's characterize it. Let's put it in the right context. And then let's go find the right solution for it. And by the way, when we go find it, let's make sure that we don't get too attached to any one particular pathway until we're sure that we're sort of on the right way. So that's sort of the founding story of Form. And I think it's important because it really has, and all 5 co-founders are still very much involved in the company today. We don't hate each other, which is maybe a fantastic, more than that, we really like each other. And that's a testament to the unifying principle of working on a hard problem that you believe deserves to be solved, and putting that as the North Star for sort of all the interactions. So the founding team kind of comes from all over, from academia, from other battery companies, but we all had battery experience. None of us was, a neophyte about this or had unrealistic expectations for how long it would take or how hard it would be or how much money it would take. And that also is what allowed us to really dig deep and pull through some of the hard times that we've been through. And as a result, we've been able to raise the capital that we need. So, capital is not to be taken for granted. We've raised $1.2 billion in equity capital to date. We also have about $600 million in non-dilutive grants from the state of West Virginia, as well as from the U.S. Department of Energy. And it's a wide range of investors, as you might imagine. Early stage climate tech investors to large, what are called crossover funds. Literally $1 trillion asset managers, and sort of everything in between. And that's really what it takes to kind of get to where we are today. So that we're about 1,000 people, by the way, in those 3 locations. We started as an R&D company in Boston, 5 guys really working in a lab. And we expanded to engineering in California. We have about 250 people there. And we are, I would say, becoming still a manufacturing company in West Virginia. So if you've never been to Weirton, West Virginia, it's sort of 40 miles due west of here, just past the airport, keep going. And it's in what's called the northern panhandle of West Virginia. And we'll talk about that a little bit more. Now that challenge that, the unifying problem that we really got together around to solve is one that is overly constrained. And that's why it is an interesting one. Right? You think about the electric grid, you're constantly trying to balance and solve between cost, reliability, and safety. And in that context, of course, in the last 10 years, we have seen some new dynamics come in. And that is load growth, that is increasing share of intermittent renewables, which provide its own challenge, and more severe weather events, which are also increasingly driving the challenges there. So in this constrained environment, sometimes sacrifices are made to sort of solve the ones that you want to meet most. Historically, that has been affordability and reliability, right? That's sort of the foundation of the electric sort of social compact that we have in the United States. But the addition of the load growth, sort of an imperative to meet that, especially driven by, of course, artificial intelligence demand for energy. And it has risen in such prominence that we now talk about energy for AI in terms of national security issues. And so it's hard to say which one's more important, reliability or affordability for everybody or national security, right? These things are sort of in tension, and we have to be able to sort of invent our way to not having to cut the baby in half, so to speak. But these challenges are very real, and they exist for every single grid operator on the system. They exist for every single one of us ratepayers on the system. And the solutions come not in silver bullets or single technologies, but really in portfolios of resources. And so into that portfolio is where we started, right? We really wanted to understand the balance of system and how it all works together, right? The grid is built from a hugely diverse set of assets. Of course, you have coal, you have natural gas, you have hydropower, and then more recently, of course, you have renewable power, right? You have wind and solar, there's nuclear in there. And now we have storage, larger and larger amounts, right? Lithium ion, of course, was the first major wave there. Actually, pumped hydro was the first major wave, going back 50, 60 years. And then it became lithium ion. And now into this mix, part of the question was, well, what type of technology helps solve this overly constrained problem in a new way? In other words, is there room for a new asset class of energy storage that solves those problems that really today can only be solved by sort of oversizing or by paying too much or by sacrificing reliability, right? And so this is sort of the precept for starting the company. The solution, and I'll come back to sort of how the solution ties into the challenge here, but jumping forward, the solution that we landed on and that we have underwritten at every major sort of inflection point of the company is iron air as a battery. Iron air, reversibly rusting iron. We're oxidizing and reducing iron. That is the electrochemical process. That is not a new chemistry. That was studied in some detail, in fact, right here in Pittsburgh by Westinghouse some 50 plus years ago under a grant that they received from the US Department of Energy. And over the course of 5 or 6 years, they characterized the chemistry pretty well. And when we were looking to solve this problem, we understood that the technical proof points that had been demonstrated over 50 years ago were good enough for a minimum viable product. In other words, if you can access the amount of milliamp hours per gram of iron that they did 50 years ago, then you could have a minimally viable product. And the bet that we sort of made was, well, we can probably take 50 years of advancement in material science and corrosion science and do at least as well as those guys did 50 years ago. And the reason to pursue all of this, of course, is because iron ore is phenomenally low cost, right? Iron is the most mined substance on Earth behind only coal, and it's in the billions of tons per year, right? Everything else is sort of in the millions or maybe tens of millions. So it's sort of iron. 3 of the top 5 mined minerals on Earth relate to steel making. There's another way of thinking about it, right? Even the small stuff that goes into steel making is larger than copper, for example. So incredibly safe to humans because it's sort of the Earth is basically a rusted ball if you squint a little bit. So humans have been around it for a really long time. As a result of the abundance, it's extremely affordable, of course. It's scalable. There's no sort of fundamental governor on how much you can scale this technology based on raw elemental abundance on the Earth. And it's because it's been demonstrated, it is a very durable anode. Specifically, the iron anode is what we use. In fact, Thomas Edison's first battery was a nickel iron battery that he commercialized going back 115 years ago. So there's plenty of literature, there's plenty of demonstrated technical capabilities for iron anodes. And we sort of put it all together and said, we're going to be the first ones to commercialize this. Now, what does that mean? It means we have to show that we can mechanistically control the electrochemistry, charge and discharge as many times as we need to, get the amount of energy in and out. And we can build a device around that that can be manufactured with high volume, with high quality, with high safety, and low cost, right? And so that's been the journey of the company. It's not enough to sort of have a benchtop device that says, oh, I got my proof points, I'm done. That's really when the work starts. For Form, that was about, in a 9-year journey, that was about 7 years ago that we had something on the benchtop that we thought, yeah, that performs pretty well. We like the entitlement there, right? And all the hard work since then has been to really commercialize it, turn it into that device that makes sense. Where are we today? It is what you see here. It's a containerized system. It contains electrodes that we make out of the factory from powders all the way into cells. And then, of course, the finished module and system that you see here. The high-level specs are that it's rated at 100-hour duration. And that 4-day duration, 100 hours sounds nice and round because, we're humans with 10 fingers and, our system numbers, corresponds to that. But really what more than numbers of digits that we have that it corresponds to, it's the duration of a weather event that drives the overall system sizing and therefore cost and reliability of the electric grid, right? And every geographic region has this duration of weather signature. Think about a heat dome or a polar vortex or a sandstorm or a hurricane. It doesn't matter where you live, you have that duration of a weather signature event that drives your system cost and reliability. So that's where the 100 hours comes from. And by the way, that was something that my co-founder Marco Ferrara pinned down very precisely in very complex co-optimization software that he built. It wasn't just a finger in the air. Intuitively, it feels like we should hit that. There was a lot of work that went into that. And we thank Marco for sort of building out a treasure map, if you will, of that duration and then all the other specs that go in there. Round trip efficiency, cycle life, all the important parts for a battery. As far as what else it has to do, it has to be available more than 90% of the time. In order to be a capacity resource on the electric grid, you must be available when they need you. This is maybe axiomatic and it sounds simple, but you have to design a device that actually embodies that capability, and you have to prove it in the function of the system. And so meeting that requirement has been, from the very beginning, the mindset of the company. We aren't so much, as we say internally, we're not so much building a battery as we are building a bankable asset, right? It is an asset class, and we really do have to think about it that way. If I could remove the term battery from every piece of literature and every way that we talk about what we do, I would. Simply because the interface to the market, no one, I'll submit something to the room. Tell me if you think I'm wrong. No one has ever wanted to buy a battery before. They may thought to themselves, gee, I wish I could buy a battery right now. No, what you want is electricity when you want it, right? That's really what it comes down to. And to our customers, the utility operators, they truly could care less about the chemistry. They want electricity when they want it, and it has to be at the right price, right? And so that it's a mind shift for thinking about the product you're selling that we had to go through, as a company, going from R&D to commercialization. But we really have to think about our resources, our product as a capacity asset, a firm capacity asset that is available more than 90% of the time, as much more than simply a battery, a neato electrochemical device, right? Now, for any of this to matter, you have to be cost competitive. And again, back to the iron air, this is part of the whole point. $20 per kilowatt hour was always the figure of merit that we aimed for. When Marco, my co-founder, built those sort of complex co-optimization models, 100 hours comes out very cleanly in the math. Therefore, then the dollars comes out very cleanly in the math because duration and cost go hand in hand, right? They're inversely related for storage. And $20 per kilowatt hour at 100 hours is $2,000 per kilowatt. That's what you need to be in a clearing price to be competitive with all the other commensurate resources in the electric system. So that was always the mark on the wall. And now we're starting to scale that up because we have that in line of sight. But that $20 has not changed. When very shortly after we founded the company, that became the mark on the wall. And that is what we sort of announced to the world when we said, this is the chemistry we're pursuing some 5 years ago. And we remain convinced that key figure of merit is what will enable us to continue to deploy in massive volumes going forward. And importantly, it's no longer just an aspirational squint your eyes, look at the bill of materials and say, maybe I can get there. We have devices that are now operating that are proving that we have the power densities that are required to hit that cost point. So we see that very much in sight. It is very much on a firm technical development plan. We know how to commercialize devices from the stage that is today. And I feel very confident that before the end of this decade, we will be deploying our assets at that price point in the market. By the way, at that price point in the market, you are competitive with natural gas in every market in the world. That is a multi-trillion-dollar market. That's the whole point, right? That we started the company for. That's why you take a big swing. It is not to end up on first base. It's to hit a grand slam at the bottom of the ninth, and that's what we're aiming for right now. We like our chances. Breaking it down just a little bit more, so you sort of have a mental map for what this consists of. The first article on here is cell, but actually it starts with the electrodes. As I mentioned, we make from powders that come in. So we receive super sacks, 500 kilogram sacks of iron powder come into the factory. We receive carbons, we receive binders, we receive all sorts of different things that go into making the two electrodes that we produce on site, that iron anode, and then the discharge cathode. The discharge cathode is also known as a GDE, a gas diffusion electrode. Some of you are probably familiar with this. It's a Gore-Tex with a reaction happening in the middle. We have liquid on one side and air on the other, and you've got to maintain that triple phase boundary with the reaction for more than a decade. And this is a technology that we actually acquired from another company at the very beginning of the pandemic in 2020, a company called Fluidic, later Nant Energy. They were a zinc air battery company, and we didn't care for the zinc side, but we loved that work that they did on the air side. And I mention it simply because, going down this journey, it's never you just invent everything yourself at all times, especially in the battery field. And you also never know when prior research may pay off. I mentioned Westinghouse and the work that they did 50 years ago. Nant was started in the early mid-2000s, 2005, 2006, something like that. And as a company, they failed, but they spent $100 million in 10 years on just the air cathode. And it was, even as a failed company, it was the world's best air cathode. And so we had our eye on that from the very beginning. We also acquired actually a nickel iron battery company. That same chemistry I mentioned Edison had commercialized. That company also failed, but we bought it for the knowledge that they had on the iron anode side of things. So, sometimes these things pay off. You never know when the research pays off. You never know when the hard science finally shows up and has its moment in the market. And for us, we have found that it's not just picking the chemistry, but making sure that we're identifying the other technologies that are out there that have never been commercialized, but finally find their moment in this particular application. And I think in the academic setting, it's particularly important to keep that in mind when working on maybe what feels like somewhat disconnected fundamental research from the commercial sphere. Anyway, we take those anodes and those cathodes and we put them in the cells, and then we sort of assemble it from there. The whole point of every single one of these steps is to make it extremely manufacturable and scalable, and therefore able to be low cost, right? That is the mindset for the way that we design these devices, the way that we assemble them, and the way we deploy them. And this is a picture of some of those assets being deployed. This is at a site in Minnesota. This is before it got really cold and snowy when we were deploying these things. And it was a great proof point that we could deploy at a customer site. It's actually co-located with a gas plant. So behind the utility fence, there's a natural gas plant on this very location. So we had to pass all the safety requirements and the local jurisdictions for the fire department and hazard analysis and safety plan and everything else. And we successfully did that. And that first commercial deployment is always a threshold moment for a company, and for Form that was a particularly important one, no exception. Now, where are we doing all this? I mentioned Weirden, it's about 40 miles away. That is the site of an old steel mill. So if you haven't heard of that town before, it is named after the man who invented or who created the steel mill at that location. In 1906, E.T. Weir, who lived in Pittsburgh, was looking for a place to build a new steel mill. And as you probably know, flat land next to a river is not in abundance in our region. And he found that place right on the Ohio River and said, this is a great place for a steel mill. Put it in context, during World War II, it was the largest single site producer of steel for the war effort. So it was on the German bombing maps, they say. So it was a really prominent place. Of course, with the senescence of the steel industry throughout the 70s and 80s and 90s, the town of Weirton and the steel mill there also sort of fell on hard times. The plant ended up closing in the early 2000s, and where once they had employed 12,000 employees on 2 shifts, 2 12-hour shifts every single day of the week, it went quiet. And we did a deal with the state of West Virginia to bring us to that location. They passed a bill to fully fund the effort there, and the contribution was $290 million. In exchange, we were providing 750 jobs by the end of 2028. We're well on track to do that. And we're also seeing, happily, new business sort of pop up in the area as a result. It was a fallow piece of industrial sort of graveyard, frankly, for about 6 years. That somebody was gradually turning over, remediating according to the EPA, that kind of thing. And we built that building from scratch. We broke ground in May of 2023, and we had a building that was operating in February of 2024. And part of what we wanted to prove was you can do things very fast here in the United States. There's a lot of talk about how do we reshore manufacturing? Have we lost that capability? Have we lost the drive to do that? And our resounding answer to that is no, no, and no. Or no, yes, no. I forget which way I phrased it. But we absolutely can do these things here. And so that's 1 million square foot. That particular picture shows only 500,000. We've actually built another 500,000 square feet in addition to what you see there. And we're operating about half of it. And the full 1 million square feet will be capable of producing at least 500 megawatts per year. Give you a rough sense. That's a few $1 billion in revenue for us out of that factory. Of course, when you build a factory, you have to operate it. And as a battery company, the real test is when you're operating your production equipment to see if you can yield electrodes and complete systems that are performant, right? At rate, at scale, with yield, and with performance. And until you do that, you can't really say you understand your electrochemistry, right? It's sort of a fallacy to believe that you can make those kinds of claims until you're actually manufacturing at scale. As Elon is fond of saying, prototypes are easy, manufacturing is hard. And that is true. That is one thing about which he is extremely right. And so for us, the main challenge over the last 18 months since we built the factory and landed the production equipment was making those electrodes. And there aren't any shortcuts to gaining process control for very complicated processes that have Goldilocks problems in them. What I mean by that is at every single step of manufacturing these electrodes, it's either too hot or too cold. The porridge has to be just right. You can either mix it not enough or mix it too much, right? You can apply too little pressure or too much pressure, right? All of these things at every single step in the process matters, and you have to get them exactly right or you fail entirely. And what we found is that it took us about 100,000 electrodes produced. These are meter scale devices. So if you like, 60 miles worth of material flowing through the factory before we felt confident enough based on data that we can say we actually can control the processes. We have process controls, and we can produce at rate what we need to. So we finally got through that. It was an extremely challenging pathway for us. And as I said, there aren't any shortcuts other than going and producing the electrodes in the factory, and that's what we've done. And so that's why we're ready to really start to scale even further from here and deliver on the commercial commitments that we have in hand. This is what we have announced so far. There are many more megawatts that are not yet, that we haven't announced, but which we have signed. To sort of give you a rough sense, we are sold out of the factory for the next 3 years, roughly. And more backlog is coming. These are the ones, as I said, that we've announced. And you see the types of entities they are. Xcel Energy is a very large utility in sort of the Midwest of the United States. Georgia Power, investor-owned. Both those investor-owned. Dominion, investor-owned. NYSERDA and California, those are 2 grants that we've received, but they're in partnership with utilities as well. And that's because with these utility partners, we did that modeling work upfront for them to understand the value of this differentiated asset on their system, right? This weird looking 100-hour, less than 50% round trip efficient battery in their system, what is the effect of that? And they do their own modeling, the very same modeling that Marco and team had done at the beginning of Forum. They then went and recreated and confirmed back to us. In fact, we see a lot of value for this type of asset. If you build it, we will buy it. And that is what has been happening for the last 5 years. But it took, to be clear, about 5 years to develop the market in the way that we did, so that we were able to contract with our customers on the same timeline as developing this technology, which was brand new to the world. So we sort of ran those in parallel pathways, knowing that, again, it was going to take a long time for both of those things, market development and technical development. As far as for what comes from here, we're really kind of just getting started. So the first deployments, to a customer were last year. The first larger scale initial deployments will happen over the course of this year and next year, and then we'll really scale up from beyond. Internally, the way that we sort of think about the future for us is really as sort of a 3-year cadence. This year is launch, next year is optimize, 2028 is scale. And we sort of picking the right pathway through there that lets us really scale as quickly as possible. That's the ultimate goal. It isn't 1 megawatt here or there this year or next year. It really is to make sure that we are setting ourselves up properly so that we can produce as many megawatts as possible starting in 2028 and then really going from there. This is a global market. The physics are the same. The weather patterns are the same in every single country in the world. And then therefore, the solution is a global product. We'll announce our first non-US projects this quarter. And they'll be far flung. They'll be all around the world, but deep markets in every single one that we're starting with. So we feel great about the work that we've put into the company to date. As I said, it's about 9 years in. I always thought it would be about a 10-year venture before we sort of saw some material returns. And that still feels about right. But it's also a super exciting time in the company to know that we're sort of on the other side of some of the hardest technical challenges here. And we really have a capable team and a technology that has proved itself as we scale up all the way to this point. So with that, I'll just leave you here. We have a lot of open jobs. We love young, great talent. And we have our great recruiting team here. If you want to come say hello afterwards, some of them wear the Forum insignia wear. So please do say hi. And we're going to be more engaged with CMU going forward, certainly. And the plant's not too far away. If you really want to come take a look, let us know. The best way to really understand what's happening is to see the factory, right? To see the operation, to understand what goes into the final step of creating a new asset class for the electric grid and starting to deploy it. So with that, I will stop the presentation and move over to questions. Thank you.
Thank you, Mateo. That was wonderful. We have about 15 minutes for questions, and I know there are a lot of them, so I'll just start with what I saw first.
Mateo, is the value of the asset entirely in reserves that only get called out when there's a weather disaster, or do they also provide other services in between disasters?
Yeah, it's a capacity asset, which means that it is not primarily sort of moving energy around day in, day out, or even week to week. But it is used more than just sitting around waiting for a 4-day weather event to come through. Generally, the way to think about it is a combination of types of use cases. One is that, polar vortex, absolutely. Discharge for 5 days in a row, by all means, do that. The other is just tight grid conditions. In that case, you may discharge for 10 hours a day for 10 days in a row, right? You don't want to ever recharge and add any incremental stress to the system. So you're just saying, essentially act as a peaker function, right? And then the third is where you sort of have these seasonal imbalances, right? Think about today, for example. It's like the weather's not that severe. The loads are relatively light. You have all your renewables producing essentially at their peak. What do you do with that? That's essentially the month of April for most of the US anyway. And you sort of would ratchet up day by day. You're only charging 3-4 hours a day for 30 days in a row, something like that. And then the opposite of that would be more or less the month of August, where you're sort of running at a net deficit every single day. So it's sort of a combination of those kinds of things. Sometimes we see it dispatched into energy arbitrage, but that's sort of unusual cases. On the other hand, whenever a utility owns an asset, they use it. So it's not just going to be sort of an idle asset, 8,700 hours a year, right?
Hi. So grid markets currently aren't very good at pricing energy across days. It's pretty good at 4-hour charge, 4-hour discharge, but like the seasonal charging and discharging you're mentioning, it's not very good at pricing. So I'm wondering what changes might be needed, or what an ideal market pricing regime would be to support this type of technology and this need for seasonal storage.
Yeah, so let me parse a little bit of what you said there. So we refer to our sort of category of storage as multi-day duration storage, not seasonal storage. And that was one of the questions that we answer. What duration does matter? Do you need 2,000 hours of storage? Do I need to take a kilowatt hour of sun from summer and move it into winter? Is that the challenge? And what we found, again, through the math, the challenge is actually taking the resources before the storm, making them available for the storm, and then coming out successfully of the storm. Whether you're in winter or summer or spring or fall, it doesn't matter. That is the challenge. And so you bound the duration, right, then of that challenge. It's not in the thousands of hours or 1,000 hours. It really is in the low hundreds of hours. And 100 hours is that minimum duration you need to sort of solve that problem. Fundamentally, what that means is you're providing a reliability asset to the system. And the reason we've sold to integrated utilities is because they can price reliability. They run their own internal models. What you're referring to, the market, is sort of the wholesale electricity markets, right? Not every market in the United States operates on a wholesale electric market. So you have these, in case you don't know, it's a very heterogeneous utility market out there in the United States. There are more than 3,000 utilities. There are 50 states. Each state has its own regulatory environment for energy policy. The states are intended to be the labs of democracy, as the founders called them. Turns out they're also the labs of energy policy. And so we sort of get to see all these experiments, flowering across the United States. And so in the part of the country where the integrated regulated utility exists and runs the market, they understand the value of reliability because the CEO loses their job if they suffer blackouts, right? I'm from California. A governor was recalled because there were blackouts, right? Politicians lose their jobs because of blackouts. So those integrated utilities who are responsible for absolutely everything, generation, transmission, distribution, retail rates, they price reliability very much so. And because they price reliability, they can put a price on our asset. And that's why we have been able to successfully sell to them. In these wholesale markets, they are imperfectly designed. And you heard I was an economist, or I have a degree in economics, did different things. But even basic understanding of economics will tell you every market is imperfect in some way. And the design of the electricity market is particularly imperfect. And the reason for it, from my perspective, there's two main reasons for it in the US today. One is there is no product for reliability. Nobody is compensated for reliability in the wholesale market designs that exist today in the United States. No one. The other is we're trying to reconcile two systems that were in a market design that only contemplates one of them. In other words, the fuel-based system. So you think about the history of the United States grid, primarily fossil fuels or maybe some hydro. And in that case, you have fuel that you're paying for. And so your marginal cost is not zero, essentially. Your CapEx is relatively low. Your fuel cost is meaningful. Now we enter the world of renewables. Now your CapEx is relatively high, but your fuel cost is zero. Those would imply two very different market design approaches, right, to sort of optimize for capacity and reliability and cost and everything else. And yet we have one system that's trying to sort of kludge these two things together. And so we end up with lots of patches that are very, very imperfect in the market designs. So I think in the end, we do get to a point where we're able to articulate the value of reliability for the system, but we are definitely not there yet.
Hi, thanks for a cool talk. I have a sort of materials end question. So iron to iron oxide is a pretty big volume change, right? And I'm curious, to the extent that you're able to talk about it, how you kind of engineer around that in your actual device design, so that you don't just rust flakes off of things, so you don't lose a bunch of your active material all the time as it's cycling through this pretty large change in the properties as it reacts back and forth.
Yeah, that's a great question. Of course, that for those who are not familiar, when you come across a rusted piece of a bridge or something and you can flake it off, that's precisely because of that volume change, right? Sort of the layers that are created with the oxygen coming onto the iron. The way that we solve that challenge is through porosity. So our iron anodes are about 60% porous. So that volume expansion happens inside the pores and over the surface area of the system, which means that we have to engineer that anode, right? So I said, what are the challenges of producing things from powders to get the right, morphologies, to get the right performance? That is one of the challenges, right? How do you do that? And then how do you access inside of that porosity, right? Because you're going both directions, so you're not just going one direction. And so a ton of engineering and material science has gone in to solve that problem, right? But that is one of the core challenges of producing iron anodes. And we see directions even further down the line for the next generation of the product that removes those challenges entirely, which is really, really fun. And since it sounds like you're sort of in this space, that when we started the company, the theoretical limit that was understood to be the case for accessing the iron to iron hydroxide, which is actually the first reaction, is 960 milliamp-hours per gram, something like that. And we had experiments where we were getting more than that out of the reaction. We said, what's happening here? We don't really understand what's happening. And so the team really dug into it. And it turns out through some very innovative additives that the team had come up with, we were going we were bypassing that first reaction. And now we have cells that are on test that are performing higher than 1,000 milliamp-hours per gram. Wow. Which is fun. Like, Form learned something about iron, which had never been discovered before, and that's kind of remarkable given how long humans have been playing with iron. So all that to say, the frontiers are far from fixed, right? We can plunge into these topics that we think are well studied or well characterized, and it turns out there's plenty of room to run yet.
Very cool. Thanks.
Hello.
Yeah.
I have so many questions. I'm just going to ask them all, and you can decide which to answer. So first, you mentioned how reliability doesn't have monetary incentives in the current market design. And from what I know, transmission and distribution actually has like a disproportionately larger impact on total system reliability rather than peaker plants or power plants in general. So are you targeting more centralized systems, or would building like smaller decentralized systems kind of take advantage of the reliability you offer but overcome the T&D limitations? That's question one.
Okay. Yeah.
Two is, what does end-of-life management look like?
Yeah.
And then three is, do you offer tours of your West Virginia facility?
I guess so. So there's no standing tour option. We do have a museum in the factory that is open to the public. And so if you go to the museum, you can see sort of the history of the site. We have artifacts. We have beer cans that they produce there. There's actually still filled with beer from when they made it, 60 years ago. And so we really want it to be an open place for the public to come in. As far as reliability and where it sits on the grid, yes, the majority of outages do come from distribution level equipment, essentially burning out, right? Transformer blows, and that's what people experience. But the reliability events that cost people jobs happen at the generation level or the high voltage transmission level. That said, the product, right, iron battery, it can be made to be smaller. It is possible to envision a residential or small commercial product. And so that's down the line. We need to sort of, get through the first phase of where we're at, but absolutely that's a sort of natural extension there. And hopefully we'll have some fun stuff to talk about down the line. And then end of life. So there's a remediation plan. You can, of course, there's nothing wrong with the iron at the end of life. It's either oxidized or reduced, depending on which one you want, and you can put it right back into the iron feedstock. And then, the rest of it is plastics. You can recycle those. So there's really no path for a new product in the market that today does not have an end-of-life plan to it. So that's sort of de rigueur for every project that we sign.
Thank you for the interesting talk. I'm curious if you're able to speak on this. Like, what are you using to reduce the iron? Like, what's kind of like a temperature range of if you like the thermal cycle, and if there's how do you deal with you mentioned a little bit, you talked a little bit about the flaking of the oxide, fines, or like the changing kind of morphology of it as you like reduce and then reoxidize? Like, do you see any changes in like the porosity or like the reaction kinetics of like how much gas you're able to get through the cells and all that as you cycle over and over again?
Yeah, there's a lot of questions there.
Yeah, sorry.
Just to take the first one, the temperature is just sort of ambient temperature. So the reduction of the iron, to be clear, is happening in an aqueous environment. So it's fully submerged into it's a potassium hydroxide is the solution, and then we have some other additives in there. But it's just happening at ambient temperature. The loss of efficiency mostly manifests as heat, so it does heat up a bit. But we're talking sort of staying in the 30 to 40 C degree range, right? So you're not. This is nowhere near like the reduction environments for natural gas, DRI or anything like that. But I will defer the other questions. There were a lot of questions there, but maybe I'll skip those for now.
Given your vantage point of having a view of all of the different public utilities and state regulatory environments out there, if you had a magic wand to be able to change policy, what would you do?
What would I do? I would have a central omniscient planner for the entire grid for the United States. I'd build a lot more transmission. I would build a lot more storage. And I would have integrated energy policy for the entire country. That's how you get to the least cost. I mean, you can do it. The path that we've picked, it works, right? Generally, it's not optimized. That's for sure. It's not optimized for cost or for speed, frankly. Those are the trade-offs. So if you could do it, you can do it at the whole country level. It's totally possible, right? If I had one, that's what I'd do.
I'm curious about your slide up here and your workforce specifically in West Virginia. I see that all of these are engineer jobs, I'm assuming because of this audience. I'm curious sort of what the mix is in West Virginia of sort of shop floor, no post-secondary education versus this. And like, how has it been for you to recruit and train those people? Is that an uphill battle for you, or like people are pounding on your door that are qualified?
Yeah, so we have about 400 employees at the factory today. About a third of those, a little bit more than a third of those, are non-exempt employees, so hourly workers. That number will grow as we continue to sort of ramp up the factory, and we add shifts and we add additional lines and that kind of thing. The fantastic talent team here has done a number of job fairs and sort of open postings for jobs. We have way more applicants, qualified applicants, every time we do that than we have slots available. And we have a workforce that is extremely well trained in industrial environments, being safe, working around equipment, and they're great. So we have had no trouble filling those types of roles, certainly at the factory. In fact, we have a good number of folks who used to work at the mill when it was around, 20 plus years ago. The other, the engineering roles, we recruit from all over. You do have to, cast the net decently wide to find the specialty sort of skills that we're looking for, process engineering and manufacturing equipment and, that kind of thing. So we recruit from the places you would generally expect, but, Pittsburgh has its charms, of course. And so what we always try and do is get people to come and see for themselves. I think most people have an outdated notion for what Pittsburgh or what West Virginia is. Versus what it actually is today.
Hi, first a great talk. It's really cool to see all this work. My question is, having gone through kind of the major steps of manufacturing now, are there any areas that you wish would be, or like any technology areas that you wish would be receiving more attention on the research side? On like the either material development or like areas like that?
I mean, there's so many areas. Oxygen reduction reactions are always of interest, right? To get those to be more efficient at ambient temperatures and pressures. But partially to my comment earlier, you never know where the flower is going to bloom. And I think, rather than, if I could dodge your question a little bit, I would rather that there are more people who are just fully pursuing their curiosities. Like whatever really gets you motivated to dive into a topic, that should be the thing that you work on. Not what somebody else says is like of interest, commercially or relevant to, my own particular line of thinking. I think it's really more a curiosity-driven passion for research. That's more important, frankly. If I think about like, those technologies that we picked up, along the way, I know some of those folks who worked on those technologies that didn't go anyway, and they don't regret for a second that it didn't become commercial. They dug into the thing that they really wanted to dig into. Is it nice to have like commercial applicability from day one? Sure, but you also don't know like how the winds shift or how the market shifts, and so trying to predict that in a research lab, I would say should not be at the top of the list.
These have been wonderful questions, and unfortunately, just given the interest of time, we have time for one last question. But after this, and after we give our distinguished speaker a round of applause, I encourage you to come up, introduce yourself, and ask any follow-up questions. We just want to make sure we have Mateo out on time.
I'll come back to the aspect of workforce, which is related to my research area. And I'm curious about, because you talked about that for some roles, you've received so many good resumes, but I'm curious about, are there any roles or positions that the company is having difficulty to hire enough qualified people from local? And what are they? And if there are such roles or positions, to what extent are you willing to hire people from not qualified people from other area that are willing to make a transition into this area? Like maybe after they make a transition and you will give them some training. And I'm wondering about the process and the extent the company is willing to accept such workforce. That's my question.
We certainly there are some specialty engineering roles that we have to sort of cast a wide net for. I would say primarily those are on the electrode process manufacturing. So these aren't just sort of run of the mill, if there's such a thing, mechanical engineers or chemical engineers. These are people who specialize in production of active cathode materials, right? So generally coming from the battery space. That's generally what we see there. There are some related industries there, chemical industries, processing industries, but generally that's the hardest sort of workforce to identify and locate from here, and that means we are going a little bit further afield for those particular roles.
Well, Mateo, this has been a truly inspiring hour for all of us, myself included. So we really look forward to watching where Form goes from here. But everyone, please join me in giving Mateo a round of applause. Thank you all for coming. Please join us for our next lecture happening on the 24th next week, and also for Energy Week. And on your way out, if you still want some food, please grab some. Thanks, everyone.